Hello everyone, thank you for listening to my talk and welcome to my presentation. My name is Patrick, I'm a final year PhD student at Imperial College in London under the supervision of Michael Hood. And today I'm going to talk about detecting credential theft by learning access behaviors to LSASS. This is a joint work between Microsoft and Imperial College, and I'm very thankful to Rodney, Tim Burrell and Joshua Neal from Microsoft who mentored me and offered me the opportunity to work on this project with them. As the title suggests, our work focused on studying a particularly sensitive area in memory on Windows machines called LSASS. So I will start this talk by introducing this process and its importance in intrusion detection. I will then present the methodology that we followed and the results that we obtained. In the third section, I will go into detail about the type and the amount of data that we collected, the classification method that we used, and the detection algorithm that we derived. This will lead me to present the performance of our detectors in terms of true positive and false positive rates on regression tests, and I will also demonstrate their effectiveness on real data. Finally, I conclude the talk by discussing some potential ideas that could extend our detection method to interesting and more general scenarios. First of all, I'd like to introduce Microsoft Defender Advanced Threat Protection, which will be referred to as MDATP in this talk, for two important reasons. First, this research has been conducted on data that was provided by MDATP. And second, the outcome of this research was to produce a detector that is now running on production and protects MDATP customers. MDATP is an endpoint security platform designed to help enterprise networks detect and respond to advanced threats. Sensors embedded in Windows collect and process signals from the operating system and send this data to a private cloud instance of MDATP. Part of MDATP's responsibilities is to process this data and to translate these signals into detection and recommendations that can protect customers. The aim of this talk is to present one of those detection mechanisms that we have recently been working on. For the scope of this project, we focused on a particular type of sensor data, that is the memory read accesses to a precise process called LSASS. The Local Security Authority Subsystem service, referred to as LSASS, is a system process that is in charge of enforcing security policies on Windows machines. Its responsibility include verifying user login, managing passwords, and creating access tokens. And as such, the memory of this process contains sensitive data and is thus often targeted by attackers, as the data it contains may constitute a means of privilege escalation or lateral movement. These observations constitute the basis of our detection method, as our first reasoning was that a process which accesses the memory of LSASS may be trying to get some sensitive information to perform an attack. However, we noticed when first exploring this avenue that the memory of LSASS is also scanned around 40 million times a day over all the machines on the ADATP network. So the main objective of this research was to try and answer the following question: how to distinguish a malicious read from a legitimate one. In order to do so, the first step that we took was to process our input data as follows. For each machine which runs MDATP, we decided to aggregate all the memory read events from LSASS performed by a single process over a 5-minute window into what we call the read session, and which we further characterized by the two features: the total number of bytes read and the total number of read attempts during that 5-minute window. As hinted at earlier, the volume of data that we received that way was around 40 million read sessions a day. In order to be able to identify the read events that have a malicious intent, we set apart from all the memory reads collected on MDATP machines those that were performed by Mimikatz. Mimikatz is a popular credential dumping tool that reads memory from LSASS with the aim of retrieving sensitive information on a targeted machine. This enabled us to have a source of common attacks, as we gathered a total of 360 Mimikatz instances over 3 months. The next step was to visualize and to try to identify patterns in both the legitimate and the malicious data that we had just collected. We then aimed at classifying the malicious data more precisely by means of logistic regressions, as we'll see in the next slides, for the three most popular credential theft techniques that are implemented by Mimikatz, which are pass the hash, stealing logon passwords, and enumerating Kerberos tickets. Finally, to conclude the overview of our procedure, we trained our classification model on all Mimikatz instances that we collected over 3 months in order to build our detector. In order to evaluate the performance of our detector, we collected 3 other months worth of data in order to see how many instances of Mimikatz would be effectively spotted. And our detector detected 105 out of 110 test instances of Mimikatz, which yields an excellent 5% false positive rate. We then wanted to see if our detector had a decent false positive rate, and for that we let it run on another 40 million read events and fired only 17 alerts, which yields a false positive rate with an order of magnitude of 10 to the minus 6, which is acceptable in MDATP. We also let our detector run on the daily data that MDATP ingests, and we were able to detect interesting cases that other methods are not able to detect, which we will see in the last section of this talk. Finally, this detector is now customer-facing and protects MDATP users worldwide. Now that we've presented an overview of our methodology, we're ready to have a closer look at the actual data. Let's start by having a look at a sample of the 40 million read events that we received on a daily basis from the machines that run MDATP. In this graph, each data point represents a read session that is characterized in the x-axis by the total number of bytes read during the 5-minute session, and the y-axis displays the total number of read attempts. From that graph, we can see that there's a clear correlation between those two features, as all the data appears to be aggregated into 4 different clusters, which moreover seem to be linear. In order to have a better understanding of that data, it was of interest for us to label each data point depending on the process which performs the read session. By doing so, we noticed that all the read sessions performed by the same process seemed to be producing data points that were all lying on the same line. For example, we can see that the data points produced by the process called collect guest logs and highlighted in light blue seem to be lying on the same line. Similar observations can be made for other processes. We can notice that the 5 processes whose behavior was reported in this graph, and which are the 5 most frequent processes that read memory from LSASS, are system processes or security software that run on Windows machines and are totally benign processes. What we were particularly interested in was to study whether or not those interesting patterns could also be found in malicious data. As announced in the introduction, we thus decided to focus our attention on a particular process called Mimikatz, and that is known for reading LSASS memory with the aim of stealing credentials. As hinted at earlier, we collected 3 months worth of malicious data over different machines that run MDATP. We then displayed this malicious data as a function of the same previous 2 features. We noticed that most of the data points were lying on 2 distinct lines that we can see on the right-hand side of this graph. This was an encouraging observation since it could already help us to identify malicious data, but we were really curious about being able to give an informed explanation as to why the data is divided into 2 lines. Interestingly, we were able to refine the information that we collected about those read sessions on top of the previous 2 features and the name of the process that performed the read session. We were able to retrieve the command line that launched the process. And these contain very interesting information concerning the type of attack that Mimikatz performed. Indeed, as we can see, some read sessions were intended at stealing login passwords, while others were aimed at performing a pass the hash. A third popular technique that does not appear in the screenshot was to enumerate Kerberos tickets. Now, the interesting thing is that when labeling the malicious data depending on the attack that was performed, the correlation between the data point and its membership in a given linear cluster becomes clearer. Let's have a look at the graph that we obtained that way. First of all, we cannot see clearly on this graph is that the large majority of the data points are located on the 2 lines that lie on the right-hand side of this graph. The other data points that lie in the lower left-hand corner of the form a small minority which we decided to discard for the sake of our analysis. By looking at the remaining data points more precisely, we can see that the read sessions that aimed at enumerating Kerberos tickets or at passing the hash lied on a single line, while those aimed at stealing login passwords lied on another line of their own. Based on that observation, we were really optimistic about being able to characterize each of the attacks precisely, and we decided to zoom in on the data that correspond to each of the single techniques one by one. Let's first focus on the technique which is stealing login passwords, and let us describe into detail the steps that we followed for characterizing it. First of all, when zooming in on its corresponding data points, we observe that those points are relatively aligned, and as we also noticed in the legitimate data. One could actually argue that we can distinguish two distinct lines here, which we will discuss towards the end of the presentation, but for the sake of simplicity, we assume that the points were aggregated on a single line, and our aim was to characterize it more precisely. We thus performed a linear regression with the least squares method in order to derive the equation of the line that best fits the data. We also computed the 99 and 95 confidence intervals, which we highlighted in the green and red dashed line respectively. The idea behind computing those intervals was to visualize how well we would be able to capture the malicious data points. Then the intuition for the detector that we built is simple. If a newly ingested data point lies within that 99 confidence interval, then it will be spotted as a malicious read session which tries to steal login passwords. Otherwise, the data point would not be considered as malicious. The effectiveness of such a detector will be discussed in a few slides. But just before doing that, let's have a quick look at the two other techniques that we studied. The case of enumerating Kerberos tickets is extremely similar. We plotted the data points corresponding to that technique, we performed a linear regression and computed the corresponding confidence intervals, and visualizing these two objects on this graph endorses our intuition that we should be able to isolate most of the malicious data points within the 99% confidence interval. Finally, we performed a similar approach for the technique which is called pass the hash. This time we obtained two straight lines and thus treated them separately, following the exact same method. Regression line first, and then confidence intervals. Something that is worth mentioning is that in these illustrations, we only displayed the 99 and 95 confidence intervals, and notice that the 99 confidence interval seemed to be a decent choice, at least visually. But of course, letting the width of the confidence of that detection interval vary influences both the number of malicious reads that the detector effectively detects and the number of legitimate reads which the detector erroneously classifies as malicious. We thus computed the true positive and false positive rates for different interval widths, and the 99% confidence interval, which corresponds to a width of 3 standard deviations, indeed seemed to be a good trade-off between, as it provided a high true positive rate while ensuring an acceptable false positive rate, which confirmed our visual intuition. In order to test the detector that we had just trained, we collected 3 other months worth of Mimikatz instances and ran our detector on those instances in order to test its effectiveness. Our model correctly identified 105 out of 110 malicious reads, which yields an excellent 5% false negative rate. In order to evaluate how well our detector was able to distinguish between a malicious and a benign read event, we let it run on another 40 million read sessions that we collected over different machines running MD80P. After whitelisting 3 well-known benign software, our model raised only 17 alerts, among which 3 Mimikatz instances were found, which yields a false positive rate with an order of magnitude of 10 to the minus 6. This is an acceptable false positive rate for MD80P to be shipped on production, as MD80P has other ways of filtering out those false positive, in particular by combining signals coming from other detectors. To further demonstrate the effectiveness of our detector and the added value that it brings, I'd like to show you a few examples of interesting true positives that it raised. On the top right-hand corner, we can see an instance of Mimikatz that has simply been renamed. This instance was also detected by other antiviruses and spotted as malicious by VirusTotal. So that's not a very interesting example. Indeed, the internal file name, the file hashes, and the company name, which haven't been changed, can easily be recognized as Mimikatz. More interestingly, on the bottom right-hand corner, we can see what we suspect to be an instance of Mimikatz that has not only been renamed, but which also has been customized and recompiled in order to erase any trace of Mimikatz. The internal tags that have been replaced by suspicious Microsoft Windows, and the file hashes have been changed so that malware detectors are not able to detect this as a harmful process. In comparison, our approach that focuses on the memory read behavior of this process was able to detect the behavior of this process as malicious and likely to be trying to steal credentials. Finally, in the bottom left-hand corner, we can see an instance of Mimikatz which has been remotely invoked by PowerShell. On the target machine, the only process that runs is thus PowerShell and is considered as a benign process by common antiviruses. This remote invocation is thus not recognized as a harmful event by other detection methods. Again, the interesting thing about our approach is that it's able to detect this activity as malicious, as it focuses on identifying the behavior of the process rather than on identifying the process itself. Before concluding this talk, I'd like to mention that other factors may influence our approach and may require a closer attention in the future. We noticed that the memory read behavior of processes are dependent on the Windows version on which they run. In particular, in August 2019, an important OS update was released and it shifted the read behavior of Mimikatz by quite a bit, which required us to update our model for detection. This raises interesting questions for the future, as we may need to find ways to adapt our detection model to the OS updates that Microsoft releases. That may require anticipation and may also involve online learning. Finally, and as hinted at earlier, the detector that we presented in this talk has been shipped to production on MD80P and protects customers worldwide. This slide shows a screenshot of MD80P customer's interface when an alert is raised. You can see that MD80P informs the customer that a potentially harmful incident has occurred. It displays a short description of the attack and advises the customer with a list of recommended actions to protect herself. To sum up, we analyzed common read access behaviors to LSASS. We modeled credentials theft by a set of linear regressions. We tested our detector and confirmed that we obtained low false positive and false negative rates, which made it possible to turn our detector customer facing. Finally, we showed that our approach is able to detect malicious reads that common malware detectors are not able to identify, and that our approach is also able to classify specific techniques precisely and thus to better inform the customer as to what follow-on action to take. Lastly, I'd like to mention some potential ideas for the future, which I believe may spark interesting research. Based on the knowledge of the approach that I've just presented, an attacker may try to perform random memory reads in order to thwart our model and to bypass our detection mechanism. In order to alleviate this problem, it would be interesting to refine the telemetry that we get from MD80P in order to strengthen our detection. Another idea that I believe may be fruitful is to study the read access behaviors of other memory locations. That may in particular be the memory of web browsers, which certainly contain very sensitive information. That may also mean adapting our approach to sensitive parts of memory on Linux machines. On that note, I'd like to thank you very much once again for listening to my talk. It was a pleasure to present at this year's edition of the RAID conference. And I'd be more than happy to discuss any ideas you may have or to answer your questions should you have any comment or suggestion. Feel free to ask straight away or to email me after this session for follow-up. Thank you very much and I hope you enjoyed the talk.